Today we're going to be talking about linear programming. It's the first part of our 6.6 section. It's a continuation of our systems of linear inequalities. So what we're going to do is we're going to look through some applications in business and economics that we're going to be trying to optimize. So we're looking to try to optimize either a profit function or minimize a cost function so that we can spend the least amount of money, or if we're maximizing a profit function, make the most amount of money. And we're going to look through something called linear programming that helps us. So what we're going to do is we're going to graph a system of linear inequalities. And we're going to look for our solution set, and that's called our feasible region. So our feasible region here is that solution set, and it's going to occur where all of those feasible solutions are. So every potential XY pair that could work for our system of inequalities. And there is a there is a theorem that says if our feasible region is bounded, so it's enclosed on all sides, then one of the vertices of that region will have a maximum and a minimum for what we would call our constraining equation. So that's what we're going to be looking for here. So we're going to have some sort of constraining equation or some sort of constraining function, usually like a profit function or a cost function. And then we'll have these restrictions, these inequalities, that's going to give us that feasible region. We're going to try to find the endpoints, the vertices of that region. And that's where we're going to have both the max and the min. And so depending on our situation, we're either going to look for the maximum or for the minimum, or sometimes for both. So when we're going through this, we have that constraining our objective function here. It's also called the objective function as well. That's what we're going to actually call it more often. So we have our objective function here, and that's what we're going to try to either maximize or minimize. And then we have these other constraints. So we're going to develop these systems of linear inequalities, and what we want to do is we want to sketch that region that's corresponding to our constraints. So that's sketching that system of the linear inequalities. So we're looking for where all of those shaded regions overlap with each other. And then what we're going to do is the next step is we're going to look for where our functions or where our vertices are. And we're going to list out what all of the vertices are. And then we're going to test them. We're going to take those vertices and we're going to plug them into our objective function. And we're going to list off what each vertex gives us for that objective function. So let's say we had a vertex at 0, 0. Then I could say, well, the objective function there is equal to some number. And let's say I had a vertex at 0, 1. I could plug that in and get another number. And I would want to figure out where the highest and the lowest, where the maximum and the minimum values are. And they will exist if it is a bounded region. If it's an unbounded region, it may or may not exist, but if it does, it will occur at a vertex. So we're going to go through this example here. We have this objective function, and we could think of this as either like a cost or a profit function, but for us it's just going to be our objective function. And that's what we're going to try to maximize and minimize. We're going to try to find those values. So we have these constraints. This is my system of inequalities here. So the first thing I want to do is I want to graph these, and we're going to do the first one by hand. So just like we did in class when we did 6.5, we did our system of inequalities. I am going to want to rewrite these so that they're in terms of y. So I can take this first equation here and I can make this negative y is less than or equal to negative 2x plus 3. So move that 2x over. And then I want to get it to be a positive y. Now the thing we need to remember is when we have inequalities, and I go through and I divide by a negative 1, that inequality symbol, so in this case our less than or equal to symbol, is going to flip, and it's going to become now a greater than or equal to symbol. And it is really important that we remember to switch that around. But now we have y is greater than or equal to positive 2x minus 3. So I want to make it into that y equals mx plus b line. That's going to be a little bit easier for me to graph. If you want to leave it as 2x minus y is less than or equal to 3, you can do that, and you can graph that using your zeros if you've done that in the past. I like to rewrite it for y because then that helps me decide shading. But I rewrote it as y is now greater than. And I can do the same thing with my bottom equation. Now this one down here, when I subtract my x, I'd get 4y less than or equal to negative x plus 24. This time when I divide through by 4, it's a positive, so I'm going to keep that symbol still a less than or equal to. But I'd have y is less than or equal to negative 1/4 x plus 24. Oops, so excuse me, we got to divide the 24 as well. So negative 1/4 x plus 6. So I want to go through and I want to graph this, and remember you can graph these as your boundary lines. We also want to remember to graph these two first here. The x is greater than or equal to 0, that's going to be that vertical line, that y-axis, and then I want to shade to the right of that. And the y is greater than or equal to 0, that's that horizontal axis, the x-axis. But I want to include those as well, so I'm going to be just keeping myself in that upper left corner, that first quadrant. And I want to graph these other two lines. Now both of these lines are going to be solid because they include the equal to. And in that first one, this one that's y is greater than or equal to, I want to shade above my line because y is greater than or equal to. And then in the second one, that last one, y is less than or equal to negative 4x plus 6. That one I want to shade below my line. So go ahead and take a minute and graph those by hand. And you should get this region here. So we do have those two extra. This is my y is greater than or equal to 0. And then I have my x is greater than or equal to 0 here. So I've got this whole region here. It's highlighted in blue. So if you've got colors, you can use your colors, or you can just color it in with your pencil. But you can see that we've got these vertices here. We have a vertex here where the two lines intersect with each other. Down where it crosses the x-axis at 0, 0. And then up where it crosses the y-axis. So I have 4 regions, 4 vertices here for potential max and mins for that objective. So what we want to do is we want to list off what all of these vertices are. And some of these are going to be pretty easy to list off, like the one at the origin. So I have the vertices 0, 0. And then typically the ones that intersect at the axes, the x and y axes, those are pretty easy to pick off. Now one of them is slightly easier than the other. This one up here where it hits the y-axis, that's crossing over at 0, 6. But the one down here on the x-axis, that one's a little bit trickier. It looks like it's passing exactly through 1.5, but I do want to double check that. So I do want to check that with my equation. Now this one is going to be the equation that y is greater than or equal to 2x minus 3. And so we can do a quick little check. If I plug in 0, because I do know that's where my y value is going to be 0 at that point down there. If I plug in 0 to y and say, does 0 equal negative 2/3 x? Excuse me, I'm thinking of the other equation. Negative 2x, oh, excuse me, so sorry. Does 2x minus 3 equal 0? Does x give me the positive 1/2? So I would add 3 to both sides. 3 equals 2x. So 3 over 2 equals x. Well, 3 over 2 is just 1.5. So it is what we think it is, but we do want to be careful when it's not crossing exactly at that point that we check it. I have one last vertice, and it's where my two lines intersect. So I can use my graph, and I can say it looks like it's at about 4, 5. But I do want to quick check that. So I'm going to check that in my two lines. And I can go to that first line and say, okay, so y is equal to 2x minus 3. I can check. Does 5 equal 2 times 4 minus 3? I got a little ahead of myself there. Does 5 equal 8 minus 3? And it does. So it works for the first line. I just want to check, does it work for the second line? So my second line here is, does 5 equal negative 1/4 times 4 plus 6? Or does 5 equal negative 1 plus 6? And it does. So this is no longer a question mark. That is that point of intersection. That is my last vertex. So I have my my 4 vertices, 0, 0, 0, 6, 1.5, comma 0, and then that last one, 4, 5. So these are my 4 vertices. These are my 4 potentials for a max and a min for that objective function. So we are going to take those 4 vertices and we're going to plug them into our objective function. So our 4 vertices, remember those were 0, 0, 0, 6, 1.5, comma 0, and then that last one, which was 4, comma 5. And we want to plug these into our objective function. So our objective function, remember, that was the z equals x plus 5y. So for each of these, I'm going to plug them in, my x and my y, and I'm going to solve for z. So that first one here, my z, is going to equal 0 plus 5 times 0, which is 0. Okay, nothing too exciting there. My second equation gets a little bit more interesting. This time my z is going to equal, I still have 0 for x, but it's going to be 5 times 6, which gives me 30. My third equation, now I have a 0 for my y value. I do have an x value, that's 1.5 plus 5 times 0, or just 1.5. And then my last one down here, I have an x and a y value, so z is going to equal 4 plus 5 times 5, which is 4 plus 25, or 29. So you can see we've got some potentials. We have a clear minimum, and then we have a clear maximum, though it's close. My minimum value is going to occur at 0, 0, when my x and my y are both 0. And then my maximum value is actually going to occur when my x is 0, but my y is 6. Very close at that 4, comma 5. But it is going to occur when my x is 0 and my y is 6. So those are going to be my min and my max. Excuse me. If I want to look at not just the single smallest value, but all of my, like the ones that are always going to be at the bottom, those are the ones that are going to connect the minimum value to the second smallest. So the ones that we got from the minimum value and then the second smallest, those 2 vertices, that line segment, that's going to be the one that gives me my smallest value. So if I'm looking for the least, maybe not the absolute smallest, but the least, I'm going to look along this line segment here, the one that connects the 0, 0 vertex, because that gave us where my minimum was, and the 1.5, comma 0 vertex. So anything along that line segment is going to be smaller than anywhere else on my feasible region here. That's going to be my smallest values for my objective function. Now we're going to use our calculator. I'm going to use the calculator on the computer, which is a TI-84 Plus. If you have the color version, some of these things are going to be a little different, but the basics are going to stay the same, and we'll go over the differences in class. Here we have a new objective function. Our objective function is 5x plus 7y is equal to z. So we're going to look to try and maximize and minimize this. So we've got my system of inequalities, and I've got a lot more now. And so this is one that if I were to do this by hand would take longer. I'd have to graph 4 inequalities, find all of those overlapping shaded regions. And this is one where the graphing calculator is going to help us out a lot. So I want to rewrite each of these into that slope-intercept form because the calculator requires that. So just like we did before, we want to go through. So take a minute, do that. You can pause the video. So rewriting these in slope-intercept form, you should get these 4 new inequalities. And I do want to quick talk about this second one here, the one that's in green, and why my symbol is now a greater than or equal to symbol rather than that initial less than or equal to symbol. So if I were to take that and solve, subtract 3x from both sides, I would get that negative y is less than or equal to negative 3x plus 15. But then I need to go through and I need to divide everything by a negative. Remember, when you have inequalities and you divide by a negative, you need to flip that inequality sign. So y is no longer less than, but rather greater than or equal to positive 3x minus 15. So that's how I got that second equation in green. Only equation where that had to happen. All the other ones never had to divide by a negative, so I didn't need to worry about that at all. So here are all of my equations, and what I want to do is before I even enter these in, because we are going to use a new app, I do want to go to my window function on my calculator, and I want to set the correct window. So remember, we do have those 2 restrictions. Y is greater than 0, x is greater than 0. So that's going to give me my minimums pretty quickly. So I need my minimum for both to be 0. My maximums, though, are going to change, and my y maximums are going to be a little bit easier to find than my x maximums, because I'm going to look at those b values and whether or not my slope is increasing or decreasing, whether or not it's a positive or a negative slope. So for that second equation, the one where we had to change the inequality symbol, that was the y is greater than or equal to 3x minus 15. That one says my b value is going to start down at negative 15. Now that's not going to change my minimum. My minimum is still 0. But if that had been a positive, I would have needed to pay attention to it, like in the very last equation, which became y is less than or equal to negative 2/5 x plus 27/5. Now 27/5 is a little bit higher than 5, so I am going to want to pay attention to that. So my max is going to be at least 5, if not higher. So one of my equations starts up at 5. So I want my max to be at least 5. 10 is probably a good one. I do want to scale, and my scale is typically going to be 1, so we're going to do that. If I had a y-intercept that started at 30, then I would want my y max to be at least 30. I would want to look at whatever the highest y value, whatever the highest b value is. Like if I look at these other 2 equations here, this was y is greater than or equal to negative 2/3 x plus 3. That starts at 3, which is less than the 27/5. And then we have y is less than or equal to x plus 4. That one starts at 4, which is also less than that 27/5. So the 27/5 was the largest b value. That's going to help me come up with that y max. And I do want to go a little bit higher than that, especially since the one that starts at 4 has a positive slope. That line is going to increase. If I think about my x maximums, usually it's going to pair well with the y maximums. I can try and figure out what if I made my y is equal to 0 in all of these equations, what would the x values be? So in that first equation, if y was equal to 0, x would be 3. In my second equation, if y was equal to 0, x would be 5. In the third equation, it would be negative 4. And in the last equation, that's the key one, that last equation, if y is equal to 0, then x is 13.5. So I could hit this all the way out at 13.5. So my x max it's probably good to make it a little bit bigger and maybe go to 15. So close to the 10, but we did go a little bit larger. And my scale, I can keep that at 1. So before I do any graphing, I do want to figure out what my window should be, and I can edit that, and I can put that into my window. So the x goes from 0 to 15, my y goes from 0 to 10. And we can graph this now. But before we graph it, I do want to go through and I want to open up a new app. So we're going to use something called the Inequals app. It stands for inequality. And so in your calculators, you want to hit that app button. So your app button is right next to the math button on the, near the left, right here. It says APPS. You want to hit the apps button. And if you have the TI 84 plus silver, I don't have a lot of apps on my calculator on the computer, but you probably have a lot more. So you're going to have to scroll down a little bit to get to it. If you have the color one, the color calculator, it's about the 5th or 6th one down. But you want to scroll down until you get all the way to the Inequals app. And it ends in a Z. And you click enter. And we get this screen here that says we've got inequality graphing, which is great. This is going to do the shading for us and everything. So I can hit enter. And my screen goes straight into this graphing. And you can see if you have the TI 84 plus, we have all of these options down below that I can change the equal sign to. And in order to change the equal sign, I do need to make sure that I choose the alpha button first. All right, if I try and just click on what any of these buttons are first, it's going to go to like the window, which I still need to change in here. So I'm going to do that real fast. All right, so I've got my window how I want to, but I want to go back to that y equals. And I want to type in all of my inequalities. So you go ahead and do that. When you do want to change this, so that first one, we wanted to change and we wanted to make that into a greater than or equal to symbol. So while it's flashing on the equal to sign, I can hit alpha, and then I can go to this very last one where it says greater than or equal to, and then I can arrow off, and you can see that it's now changed from an equal to sign to an inequality sign. And if you look off on the left hand side, you can see that instead of just having a dark line, it says we're going to shade the upper side. We're going to shade the top half there. So for all of these inequalities, you do want to make sure that you go through and you change the equal to sign to one of the other ones. So those options won't show up until I scroll down and I highlight the equal to option. On the color calculator, you do need to, when you go into that y equals, you're going to have to go over one more and then click enter. So you won't have the options on the bottom if you've got the coloring calculator, the thin ones. And then it'll come up as an option. You can scroll through and choose what you want. If you have questions on that, you can just come talk to me and I'll walk you through it. But go ahead and we want to enter these all in. So take a minute, pause the video, enter them into your calculator, and then come on back. All right, so hopefully you got these in. Remember that second equation, we do want that inequality to be that greater than or equal to because we had to divide by the negative, so it switched the sign. All right, so we've got all of these in here, and so we can hit our graph. And you can see now it's going to shade. It may or may not have color depending on what you have, but it's going to shade all of these for us. And you can start to see where those lines are overlapping with each other. And we can see where our feasible region is on our graph. And so if you have the TI 84 plus, you don't have the thin calculator, you have this pops up here and it's got shades and then point of interest trace. What we want is we want to choose that point of interest trace. If you have the thin calculator, you do have to go into second calc and then you can choose that point of interest trace. But that's what we want to do. And just like before, if I'm on this screen with it on the bottom, I do have to hit alpha. And then I can choose any of the two buttons underneath it. If you have the skinny calculator, you want to hit second calc and then choose the inequality menu and do point of interest trace. And we get to the same screen here. And you can see up at the top, it's got y1 intersecting y2. That's where it's going to have that intersection of the first two inequalities. And I can arrow through these. I can arrow over, arrow up. It's being a little slow. But you can start to see those intersections. It's going to jump from intersection to intersection along the way. Now, it's not going to necessarily do the ones on the vertices because we didn't graph those, or excuse me, on the axes because we didn't graph those, but we can still find those. But it does give me the more difficult ones to find, these two here. So you can see we have these these 6 points of intersection. 1, 2, 3, 4, 5, 6. We have these 6 points of intersection. And we want to list off what they are as their vertices. So you can arrow over, and you can see as you arrow over, up at the top here, we've got that intersection of our different lines. And it's going to help us keep track. But you can see it flashing. So as we flash through, as we arrow through here, you can see it jump from vertex to vertex. So one of our vertices is at 6, 3, and we have another vertex at 1, 5. So go ahead, arrow through all of these and list out all 6 vertices for this feasible region that we have. All right, hopefully you were able to get all of these, including the ones that were on those the axes, the ones that we didn't have the lines graphed. We didn't graph the X and the Y ones. But hopefully you were able to get all 6 of the vertices that we have here. And so just like we did before, we want to list out all 6 of these, and we want to substitute them into that objective function and see which one gives me the maximum and which one gives me the minimum. So that's what we're going to do here. We've got our 6 vertices, and we have this objective function. So for each of these, I want to plug them in. So for this 3, 0, my z is going to equal 5 times 3. Plus 7 times 0, or 15. And we can do the same thing for the rest of them. So go ahead, take a minute, pause the video, plug these all in, and see what we get. So you should get, hopefully after you do all of that arithmetic, these 6 values for z, our objective function. And then you could hopefully pick out what our maximum and our minimum values are. So we have that our maximum value occurs at the point 6, 3, and it is a maximum of 51. And then my minimum value, that occurs at the point 0, 2, and that a minimum is actually 14. So all of the smallest values, again, would connect the vertice that gives me 14, the smallest, to 15, the second smallest, so 0, 2 to 3, 0. But the actual minimum is 14 at 0, 2, and the maximum is 51, and that occurs at 6, 3. So next time in class, we're going to do more examples with this, working through here. But it's essentially, we're taking that system of linear inequalities, we're finding the vertices, and then plugging that into an objective function to find a max and to find a min.